So in this question, we're going to fill in a whole ice table, and we have an initial mass of both reactants. So we don't know which one's going to run out first. That's going to be our starting plan or goal, is to figure out which one is our limiting reagent. You cannot do any stoichiometry with mass. Our balanced chemical equation says 1 unit of our first reactant is going to react with 1 unit of the second. It does not work with mass. 1 gram doesn't react with 1 gram. The why is they all have different molar masses, so they have different counts. So we have to get moles of each of our reactants. Then we can figure out which one's going to run out first. We've got a 1-to-1 ratio, so the lower molar amount is the one that's going to run out. So we've got 10 grams of each. We've got a volume of water, and that water is not going to factor into any of our calculations. The water is why we've aqueous solutions, but it doesn't affect our math. Now, I like to, as an organizational strategy, kind of do my sodium chloride underneath it and my second reactant, my silver nitrate, underneath it when I'm doing limiting excess. It's just a nice order to help sure I don't mess anything up. And I'll color code them. So the moles is going to be mass over molar mass because we have a solid, a pure substance. So for sodium chloride, that's 10 grams. And the molar mass of sodium chloride is 58.44 grams per mole for the 1 sodium in your data booklet and 1 chloride. So the amount of moles that 10 grams works out to is 0.171 moles. Again, keep all the digits in your calculator or go back to it. So that's our first reactant. I'm going to do the same thing for our second reactant. Moles is mass over molar mass. We have 10 grams. Now, silver nitrate is much heavier for every mole of it because silver is where a lot of the mass is coming from. 1 silver, 1 nitrogen, and 3 oxygen is 169.87 grams per mole. And that works out to 0.0589 moles. Okay. Okay. Those front zeros would not be significant digits. So I've written down 3 digits. Okay. Now I can sort of solve this fairly quickly. We've done the work, we've set things up, we've organized it well. We have this 1-to-1 ratio. Whenever we have a 1-to-1 ratio, the lower moles is going to run out first. So in this case, the lower moles is going to be the red set of numbers. The silver nitrate has less moles, so that's going to run out. We're going to have some of the sodium chloride or my blue set of numbers left over. So I'm going to take away all of the silver nitrate. Okay. That tells me my change for one of the chemicals. And we have this one of those, 1 sodium nitrate, 1 silver chloride. Okay. Everything is a 1 stoichiometric coefficient, so every change is going to be the same. My sodium chloride change is multiply by 1, divide by 1. So it's going to go down. How much sodium nitrate do I make? I can actually pick either change. It doesn't matter. I could pick the first chemical and go multiply by 1, divide by 1. or I could have picked the silver nitrate change and done the stoich. It doesn't matter. Silver nitrate's going to be the same thing. Again, we only see the same numbers because we have all the same coefficients. Our products are going to both start at 0, and because they have the same stoichiometric coefficient, they have the same change. The same final amount made. The only thing I didn't fill in was the end amount of extra sodium chloride. So this is our excess reagent. You might get asked how much excess reagent is left over. And you just take the I and factor in this case, subtract away the C. Now, significant figures, you're used to multiplying and dividing a lot. You keep the lower amount of sig figs. You don't add or subtract a lot. So you forget these rules, or you're not often as familiar with them. When you add or subtract, you keep the lower amount of decimal places, or digits. Sorry, not digit, places. So here we have 1, 2, 3 decimal places. Here we have 4. So we're going to keep 3 decimal places. So put all the numbers in your calculator, get that answer, and round to 3. So I'm going to keep 1, 1, and then I'm going to stop at 2. That's my 3rd decimal place. So that is the whole ice table filled out. So the theme of this and the next slide is calculations when the reaction is not 1-to-1. You'd probably only get 1 test question, maybe 2 that's not 1-to-1. So it's not going to be the bulk of your quizzes or tests. Okay. So the question is, what amount of excess reagent is left after the reaction? And we have a little under 4 grams of hydrogen chloride is mixed with a little less than 6 grams of calcium hydroxide, and this is in 100 mils of water. Now I've done the double replacement or acid-base neutralization, and now we've got to take that masses and turn them into moles. So I've done the reaction for you. Hydrochloric acid, calcium hydroxide. I tend to see a lot of errors with calcium hydroxide in both 20 and in Chem 30. Calcium is a group 2 ion, so it has a +2 charge. So that's why you need 2 hydroxides to go with it. So watch for calcium, magnesium, strontium, and their charges. Last comment I just want to make, water was one of the products, and it's in water. So we don't go water aqueous because the solvent is water, the solute's water. That's why you see the liquid state. So we're going to carry this out very similar to how we did the previous ones. I'm going to organize each reactant in a column. We have masses of both. So moles is going to be mass, divide by molar mass. So 3.65 grams of hydrochloric acid, divide by the mass of H and Cl. It's mostly the Cl. 36.46 grams per mole. And this works out to be a tenth, 0.100 moles. Now I'm going to do the same thing with the calcium hydroxide. The mass is 5.57 grams divided by the mass of 1 calcium. We've got to double the O and double the H. So 1 calcium, 2 O's and 2 H's. and that's 75.09 grams per mole. So that is 0.0742 moles. Again, I got all the digits in my calculator. So we know the amount of each, but they don't react together. The HCl, 2 units react for only 1 mole of calcium hydroxide. The hydrochloric acid is reacting twice as fast. Now, the way to kind of scale this, to treat this as a 1-to-1 ratio, okay, to factor in that this one happens twice as fast, we're going to do a little calculation to figure out the limiting reagent. So the limiting reagent is what? This is going to let us figure it out. We're not going to do math with it. It's just to answer that question. We're going to take our moles and we're going to divide it by the coefficient. Okay? So we're going to divide this by 2 because it is a 2 coefficient and it reacts twice as fast. So that's going to give us 0.050. Okay. So that's now scaled that down by 2 for how fast it reacts. The other chemical, there's 0.0742 moles, and it's got a 1 coefficient. So that ratio is 0.0742. Okay. So when we get, factor in one thing reacting twice as fast, we can sort of see now, apples to apples, which one's going to run out first. Whatever the lower ratio is, that's the one that's going to run out first. So the chemical that you actually have more of is the one that's going to be the limiting reagent. When I divide it by 2, factoring in the double speed, it's going to run out. We do not have double the amount of blue compared to the red, and that's why it's going to run out first. So by dividing by the coefficient, looking at that ratio, we can figure out what our limiting reagent is. It's the HCl that's going to run out. All of this 10th is going to go. So the question is, what amount of excess reagent is left over? So I have to figure out what the change is for calcium hydroxide. Okay. It is not 0.1. These have different coefficients, so they're going to have different changes. HCl is going to be double compared to the calcium hydroxide. We're just going to go back to required over given. Okay. So I'm going to put my little arrow in, multiply by my ratio. We were requiring the calcium hydroxide change, which is a 1 for its coefficient. The given information is this green, which has a 2 coefficient. So we have to multiply by 1/2. Okay. Okay. We would know we've made a mistake if that change exceeded the starting amount. Okay. We would have messed up on our limiting reagent, but we didn't. We started with 0.07 and we're only going to use up 0.05. So this is making sense. Okay. You do the subtraction. And there's 25 millimoles left. Okay, if I divide that by 1,000, it would be millimoles. Okay. And we know this to 3 decimal places. So that's answered our question. I'm going to fill in a few more columns, but we've answered what we've planned out. If we were trying to fill in our products, which weren't part of the question, but I'm going to, we've got two different columns that we can go back to. If we look at the calcium hydroxide, sorry, the calcium chloride, and I want to know its change, I want to make my life easy. I'm going to find a column, if I can, that has the same coefficient. So this column and this column have the same coefficient. It's a 1. So those two columns are going to have the same change. So this is also going to be 50 millimoles is going to be its change. If I want to know how much water is made, that's got a 2 coefficient. My limiting reagent has a 2 coefficient, so they'll have the same change. So it's going to be a multiply by 2, divide by 2. So that's a unity ratio. So 0.1 for that 2 columns, so it's going to be 0.1 here. Okay. So we're going to get double the water compared to the calcium chloride that's made, because they'd both be starting at 0. That's what our coefficients tell us, double the water compared to our aqueous one. Okay. So that was an example where our ratios were 1 to 2. The last one, we're coming to the end of stoich. This is your last stoich example. We've got a combustion reaction. We're going to determine the mass of carbon dioxide produced when we have pentene burning with oxygen. And we have a lot of pentene, we have a lot of oxygen, but we can't use those masses to do any type of stoich. No, it's not till grade 12 that you have to know what pentene formula is. It's C5H10. Anytime you have an ene, the hydrogen is double the carbon. So that's where the formula is coming from. Pent always means 5, but you knew that. You know a pentagon, a hexagon, an octagon. You're going to see all that come up in Chem 30. So octene would have 8 carbons, and the hydrogen would be double it. So you should know that CO2 and water vapor are your products. Now balancing this one is a little trickier. The hydrogen count is 10. And they come in pairs. You'd end up with 5 water. And when you if you put a 5 in front of the water, you're going to get an odd number of oxygen. And you're not going to be able to balance this with whole numbers. Anytime you have a hydrogen count that you divide by 2 and you get an odd number, you're going to want to double your fuel. And that's going to make the oxygen count from the water even. And it's going to let you balance your reaction with even numbers, because you have to have even numbers of oxygen because they come in pairs. So I'm going to double my fuel. This now gives me 2 times 10, 20 hydrogen. So I'm going to need 10 water. That gives me an even number of O there. I have 2 times 5, 10 carbons. So I have 10 CO2. When I count up all the oxygen, the 20 from the CO2, the 10 from the water, that's 30. So I need 15 pairs of oxygen. So we're going to have to figure out the limiting reagent where we've got this 2 to 15 ratio to deal with. But who cares what the numbers are? We're just going to divide the moles of the fuel by 2, we'll divide the oxygen moles by 15 and see which is the lower one, factoring in the different rate of reactions. So let's do that mole calculation. moles of our fuel, 152 grams. I'm skipping the formula, mass divide by molar mass. And 5 carbon and 10 hydrogen is 70.15 grams per mole. So there's 2.17 moles of our fuel. Let's look at our oxygen. Again, I'm going to skip the mass over molar mass. And we have 305 grams of oxygen. Divide by the molar mass of oxygen. Oxygen comes in pairs, so you have to double it. The fact there's 15 of them doesn't change the molar mass. Same with water, is always about 18 grams per mole. The fact we have 10 of them doesn't change the mass of water. So 2 oxygen is 32.00 grams per mole. 305 grams is 9.53 moles. Okay. So just looking at this, it's quite difficult to figure out which one's going to run out first. We have way more oxygen, but it reacts like 7.5 times faster. So we're just going to divide them and not worry about trying to figure out that 2 and that 15 in our heads. So our limiting reagent, what is it? So our first ratio would be 2.17 divided by 2. Our second ratio will be 9.53 divided by its 15 coefficient. So we get a ratio of 1.09 for our first reactant and 0.64 for our second. I really don't care about putting units in because this is just a strategy to figure out what runs out first. So the oxygen has the lower ratio, so it's going to limit our reaction. Because of how fast it reacts, it's going to run out first, given our initial amounts. Okay. Now, we don't use these green numbers for anything, because they're just a ratio undoing the stoich. Okay. They tell us oxygen runs out. So this is our limiting reagent. We put a 0 in our ice table, and then we do things just like we've been doing all units. Okay. All of this 9.53 moles is going to react away. 9.53 moles of fuel will not react away because we'd have to multiply by 2, divide by 15, and scale that down to figure out how much of our pentene would react. But we don't care. Determine the mass of carbon dioxide. So I'm not going to finish this excess reagent column. I'm going to be very efficient on this last example. Okay. We got 1 is get a column. Step 2 is our C. Step 3 is fill in the CO2 column. So we have to turn that 9 and a bit moles into whatever carbon dioxide is. Multiply by the required, which is CO2, which is 10, divide by the given. Oxygen is the given data, and that's a 15. So let's see, 10 over 15. That's like 2 over 3, a bit less than 1. So we're going to have less moles of CO2. We're going to have 2/3 the amount. We're going to make 6.35 moles. That's 2/3 or 10/15 of 9.53. So we wouldn't have any CO2 before we burnt anything. We're going to make a bit over 6. So we're going to end with 6.35 moles. Then, and this is hard as Chem 20 gets, mass of 2 reactants, scale them both by their coefficients, see which one runs out first. We're going to end with the mass of CO2, so that's mass subscript CO2. Mass is molar mass times moles. We've got to dump from our heads the previous molar masses we've used. We haven't done CO2 yet. So 1 carbon, 12-ish, and 2 oxygens at 16. That comes out to 44.01 grams per mole times our 6.35 moles. Moles on the bottom, moles on the top, they cancel, grams are left. 4 sig figs from our data booklet, 3 from our calculations, and I end up with 280 grams when I round it to the ones place. It kind of looks like 2 sig figs, but I had to round the last to a 0. So a fair bit of carbon dioxide. Again, this is exactly if you fly in an airplane and they wonder, how much CO2 does every passenger make? It's this exact math. You just start with whatever jet fuel is, you burn it, you make CO2 and water, you get the mass, and you just divide it by the number of passengers, because most of the time the airline wants to say, okay, for Mr. Curtis, how much CO2 do I produce when I fly? So take the seat count and divide it out. Okay.